Hello, welcome back. I'm Sophie. We're going to hop right into lab number 3, black hole. So we'll start with our introduction. And so the purpose of the lab was to observe circular motion through the exploration of a black hole. And the 3 key concepts that we are using were Newton's second law, the parallel and perpendicular components of net force, and then the gravitational force, or the universal law of gravitation. And so to do this, we use 2 different computational models. The first one, we are trying to find the mass of a black hole, and the second one, we are trying to avoid both the black hole and a planet orbiting around the black hole. So we're trying to avoid crashing our ship. And in both of these, the system was the ship, and the source of the force was the black hole. And then the initial results, the mass of the black hole was 1.469 times 10 to the 34th kilograms, and the initial speed of the ship was negative 9.8 meters per second. Times 10 to the 6th for the x direction, and for the y direction was positive 9.8 times 10 to the 6th. And then we'll hop into the models. So on the left is the mass of the black hole model. So you can see the orbit around the black hole, and then you can see down at the bottom of that model, the mass of the black hole was 1.4 times 10 to the 34th. And then over on the right, we have the avoid black hole and planet model. And so you can see the orbit of the planet around the black hole in teal. And then the magenta going down is where our ship is trying to escape and avoid both the black hole and the planet orbiting the black hole. And we'll talk more about how we got these 2 models in the next page. So moving on, we'll get into the experiment itself. So like I mentioned before, we are doing 2 different computational models for this experiment. So over on the left is the mass of a black hole. And to actually create these models, first we computed the initial and final momentum vectors, and then calculated the star's change in velocity and change in momentum, calculated dp/dt, and then fnet, and then dp/dt parallel and calculate fnet parallel, and then do the same for perpendicular, both dp/dt perpendicular and fnet perpendicular. And then finally we were able to calculate the mass of the black hole using the magnitude of fnet of the star position squared over g star mass. And then moving on to how we did the model for the avoid crash model was one trajectory for the orbit of the planet provided, and the other trajectory we had to find, so that was the trajectory for our spaceship falling after we lost control of our engines. So first we had to calculate the net force on the planet, and then the net force on the spaceship, and then we applied Newton's second law and the position update formula to make the planet and the spaceship move. So that is how we made our second model. And then you can see this is the code for the black hole mass model. So we started with our initial conditions, the gravitational constant, mass of the star, and the time interval. And then we were able to calculate velocity from that data. And then in the calculation loop, I know it's a little small, I'm sorry. We went through all of the steps that I described in the experiment page above, and then calculations continued all the way over on the right. And then moving into the code for our avoid crash model, you have the same initial conditions, and then we move into our calculation loop. You can pause and get a better look if you would like to see more of my code. But for now, we'll move into our discussion. So the results that I found were that the mass of the black hole was 1.469 times 10 to the 34th kilograms, and the initial velocity that is needed for the spaceship to escape was negative 9.8 times 10 to the 6th in the x direction, and then positive 9.8 times 10 to the 6th in the y direction, although you can fiddle around with those values a lot more. Just in those general ballparks to be able to get the ship to escape without hitting the black hole or the planet. And then moving into the errors that happened in my lab, I never received the code output that my spaceship had successfully flown away, but I also didn't get the error message. It just kept going and orbiting around and around, but never gave me that confirmation output. So, but you could see that the planet had flown its full orbit and the ship escaped successfully. So I'm not sure why that happened, but that is a potential error. And then finally, we'll move into the conclusions. So first of all, how are the net force and its parallel and perpendicular component different than the rate of change of momentum in its parallel and perpendicular components? They are equivalent. So you can see a little bit more of those calculations below. And then lastly, what if we wanted to take instead of wanting to take a quick look at the black hole and leave, you wanted to enter into orbit around the black hole, you would need less magnitude in the x direction and greater in the y direction than the values in part 2, so you're going down and around instead of just flying away from the planet. Thank you.